Alrighty, so we're nearing the end of the course. This is exciting. So let's see what we have. So last time on Tuesday, we didn't have a live streamed lecture. I didn't do anything for the last lecture. What I did do was give out some links. So I gave a link to two videos. Two links to the same video, really, on YouTube and on Vimeo. And that is to David Miller's YouTube video about implementing a neural network. And so that video is really excellent, and that is going to be required viewing for the final exam. I am going to ask a question. It's not going to be like a super detailed question, and yes, you will have access to that video for the final, but please have a look through that, and there will be a question about the implementation of a neural network on the final exam. Today, we're going to be talking about deep neural networks, and so I have some slides on that, and let's just jump right in, shall we? Let's not keep you for longer than necessary. So here we go. So as I said, this is lecture 20. Oh man, only 2 lectures left. We're going to be talking about deep neural networks and deep learning. These are really the AI buzzwords going around. They're not just buzzwords. It turns out that deep learning is truly excellent and does a great job at a lot of things. So we'll figure out what deep learning is so you can tell a potential employer that you know what deep learning is. Okay? So what are deep neural networks? Essentially, well, we've learned what a neural network is, right? And so a deep neural network is a neural network that has many hidden layers. That's basically it. So if you want to be, the most general form of a deep neural network is just a neural network that has many, many neurons and many, many layers, many hidden layers. But in practice, many deep neural networks have extra processing on top of just having many, many layers. So we'll talk about what some of those processing steps are in this lecture. Now, keep in mind that there's like 10 new papers published every day on deep neural networks. And there is obviously going to be a lot of types of networks like GANs or what are they called? Adversarial networks, generative adversarial networks. There's like dueling neural networks. There's so many different types of neural net solutions that are out there these days. I can't possibly talk about them all. So what I'm going to do is give like the high level overview of what a deep neural net is, some of the operations that are done in pretty much all modern deep neural nets, and talk about some of their applications when it comes to games and AI. And then that's all I really want you to know about it. We're not going to talk about their implementation or APIs or anything like that. That's going to be left for another course for you. So deep neural nets have been really popular since, I talked about this before, the Geoffrey Hinton paper in 2012 about ImageNet. And with the rise of GPU computing power, they've really made deep neural networks feasible. And I'll talk about this in a bit, but essentially, neural networks are just a bunch of dot products. They are additions. They're a bunch of numbers being multiplied together and then summed. And turns out that is the exact thing that GPUs are excellent at. And because of that, you can completely saturate a GPU with like billions of neurons or millions of neurons or however many you have, and you'll get like perfectly parallel processing for your whole neural net. And GPUs are just amazing when it comes to computing neural networks. And not only GPUs, but now a lot of things are coming with their own neural engines. So for example, a Tesla has a chip in it specifically for computing its neural nets. So a Tesla car has that. The new Mac M1 silicon has its own neural processor in it. It's crazy. Neural networks have become so prevalent that modern hardware has special built neural net computations in it. So they combine multiple techniques which are super effective in specific domains, namely in image processing. So we showed this example before of deep neural nets being able to classify these images. I won't go over this whole example, but just go back to lecture 18 if you want the explanation of this. So the first technique that a lot of deep neural nets use is something called convolutions. So if you've seen CNNs are convolutional neural networks. And convolutional neural networks are neural networks that use convolutions. I know it's a bit of a circular definition there. So let's say that we have some input image, okay? So let's say that this is our input image here in the middle. What we're going to have, let's say we want a neuron to look at something like a 3x3 image of that, a 3x3 pixel area from within that image. So what we're going to do, instead of the neuron looking at each pixel individually, we're going to apply what's called a kernel to subregions of that image to produce a secondary output that then our neurons will look at. The area that we use for this processing is called a kernel, okay? And the next neuron is going to look at a shift of that area. This is kind of improperly... I'm sorry, this is a little bit misexplained. It's not that every pixel is looked at by a single neuron, but I'll show you next in the animation. So what we're going to have here is a kernel is going to map one image into another image. So let's say, for example, we have this image down here on the right. What we're doing here in this animation is we're applying a 3x3 kernel to this image to produce a new image. So it's looking at a 3x3 block of this image, doing some calculation based on that 3x3 block, and then it's coming up with a pixel or a value for the next layer. See how this works? So over here is sort of the simple example of this, where this is a 4x4 matrix, and so you can have 4 3x3 matrices within that. So we're looking at a 3x3 area, we're applying some function to that, and I'll get into an example of what these functions can be, and then we're producing a new image based on that. So what does that actually look like in practice? What is this convolution actually doing? Well, one very popular kernel that gets applied to images is called an edge detector. So what we can do over here is we're going to take in an input image. This is a very famous image from image processing. And we're going to apply this 3x3 kernel to it. And what this will do is we'll take the 9 values or the 8 values surrounding a given pixel. And what we do is we're going to multiply this pixel up here to the top left by -1, this one by 0, this one by 1, this one by 2, this one by 1. So essentially, we're going to sum all of these pixels multiplied by these values. This one is in the x direction, and this one is in the y direction. And what this does, it's called an edge detector. So it essentially, it detects change from values on the left-hand side to values on the right-hand side. Similarly, it's going to detect change from values on the top to values on the bottom. So wherever in the original image we're having drastically changed values, so for example, if we go from black to white or white to black or gray to black or something like that, those changes are going to be represented as edges. So edges in our image where we drastically go from one value to another value, this is what this kernel is going to detect. And so what we do is we apply the kernel to the entire image. So we'll take 3x3 blocks of this original image, and what we end up with, if we apply that, is this final image here. So what we can think of is that final image is going to be like the edge detected image or something. And so when we're talking about convolutional neural nets, if we want a neural network to, for example, be able to identify features in images, it's sometimes very useful to have the convolutional part of the neural network apply something like an edge detector so that what we get out is an image which does things like only leave in the binary data of like whether or not something is on an edge or not. So someone just asked you move in 3x3 pixel groups. Yes, so on the previous slide, this is what's happening. So now that you've seen this matrix right here and how we apply that, on the next layer, the middle pixel will be equal to that dot product, okay? So if we look at here, this is how it's actually being computed. We go from the top left corner to the top right corner. All of these values get all of their values multiplied and summed, and then the output values are the pixels of the next image. Now, we're going to end up with an image that's a little bit smaller, but that's fine, right? We're just cutting off like the last part of the image, or the outside edge of the image. So when we apply that again, we're taking an image like this, and we're going to get like an edge detected image like that. Well, why is that useful? Well, it turns out that images, like patterns in images and features in images, what our brain is paying attention to also are those edges, right? So for example, if we look at this image of a car, what our brain is actually looking at is like where the object differs from the background, right? So if this was a blue car or a red car or a brown car, it doesn't matter, it's still a car. Because what our brain is doing is we're doing this little edge detection algorithm. Well, I say that's what the brain is doing. It could be doing something different. But what happens is, remember when last time we did the demo of the TensorFlow and we saw like the first layer had these lines going through it, and then the next layer was like lines of lines, and the next layer was lines of lines of lines. And so what we see here is that the first layer of our neural net, so this is the input image, maybe we pass that through this convolutional filter, then the first layer is going to detect these edges. The second layer is going to detect like two lines or like corners or small shapes like that. Then by the time we get to the end, we're actually detecting cars, right? And we can say, oh, this one is actually classified as like an Audi A7 or something like that. So that's sort of the idea of this convolution process. Something else that happens in order to enhance the values that we get out from our convolutions and from other processes is called pooling. So what max pooling does, for example, is the output from the convolution is going to produce another matrix. What does that mean? Well, we had some input matrix, right? So these are the inputs to our neural net, and we're just going to unfold those and pass them in 1D. But the output from the convolution is another matrix, right? So it's this matrix right here, this green one. So the output of applying the kernel to the blue matrix is the green matrix. So the output from convolution produces another matrix. So let's take the maximums from sub-areas of that matrix. So this forms another matrix, and that process is called pooling. So for example here, let's take this 4x4 matrix, and we're going to use pooling to produce a 2x2 matrix, and we're going to use max pooling. And all this means is that let's look at this 2x2 region up here, and we're going to take the maximum value from it. So that ends up being a 20. Up here, this ends up being a 30. This ends up being 112. This ends up being 37. And sort of in some areas, what this intuitively sort of means is that you're enhancing the most important features of a specific area of the matrix, okay? By taking the maximums within that matrix. So you're discarding some of the noise and taking the maximums there. And ideally, taking those maximums and discarding the rest of the information is going to help you to learn things about this matrix. So we can repeat that process as well. So we can do a convolution and then max pooling, and then we can not only do that, but let's say now we take the output of the pooling and apply more convolutions to it. And so this process of convolutions to max pooling can be repeated some number of times. Maybe not 100. I don't know why I put 100 in there. I think I meant to say 10. But some networks do this process of convolution and max pooling a number of times. Then we can optionally run the result of that output from another convolution and another pooling. And the final output is then run through a fully connected neural network. So let's see what this looks like in practice. Here, for example, we're going to take an input image. Let's say it's this image right here. And then we're going to pass our convolution filter over this image. And that's going to produce this next layer within that. So you take the input image, you apply the convolution, it produces the next matrix. Whether or not you want to call that an image, well, this might be the edge detected image, for example. Then based on this image, you do the pooling, okay, and you get another one, a smaller matrix. Then you take that and you do convolution on that and you do pooling on that, and then you pass the results of that in through a fully connected network, and now maybe you get like dog, cats, birds, etc. Okay, so similarly down here you have a bird image where you use convolutions here, then you do max pooling. This gets passed into fully connected layers, and then you get binary classifications. So this lecture is supposed to give you like an intuitive sense of why they do that, but not explain exactly how it works in practice, okay? I'm just showing you that different people have done this for a number of years. So for example, in 1998, LeCun et al., so Jan LeCun is a pioneer in convolutional neural networks. He's the head of Facebook AI research right now. Really nice guy. He basically used this to do classification of digits and letters in handwritten text. So this is from 1998, 22 years ago. Oh my God, that's 22 years ago. Where here you do convolutions on that, then subsampling, and then you do, they had this convolutions, then subsampling, and the subsampling is essentially pooling here. And so they did training on like millions of input images, and they got really good results. And then later on, in 2012, I can't remember which paper this is, which one. Oh, this was the ImageNet paper. They had the same thing, but they did it like, so when Jan LeCun did this, they had 10 to the 6 transistors on their chips. Now they have 10 to the 9 transistors, so the GPUs are 1,000 times more powerful than the CPUs from 14 years prior. But they're training on 1 million times more data. Okay, and when you get to deep neural networks, you really, really have to use more data than you use with standard neural networks, because there's so much training going on. There's so many weights in the matrix that you have to learn that it's really difficult to do the learning without massive computational power. All right, so here's another example from that ImageNet, where here you can see the output of the convolution, okay? So this is the output of the convolution. Here you're going to pass that through ReLU. ReLU is a type of activation function that we saw last time, and ReLU can be thought of as sort of thresholding, okay? So we saw that activation functions do the thresholding. So when you apply ReLU to just each pixel, then what you're getting out, or sorry, not each pixel, but each neuron, what you get out is sort of a thresholded image. Then you do the thresholding there to sort of, throw out unwanted data. Then you do convolutions based on that, and then ReLU again. And then you can pool that one, and then do convolutions, et cetera, et cetera. And then eventually you get some sort of classification based on that. We can see this process going forward with like human facial identification. And so at the very end of this process, what you get are features like one of your neurons might be detecting eyes, or a set of neurons, or detecting noses or ears, and then by the end you're weighting each of these together. So you have weights based on eyes and ears and noses and all those features, and they would add together to form a face, and you can say, oh, this is so and so's face, or this is so and so's face. Similarly here we have more examples of cars, elephants, and chairs, and the first few layers of features will be something that look like a wheel, or like the back of the spoiler of a car, or something like that, and by the end you're detecting entire cars. Similar with elephants and similar with chairs. These networks can get very, very large. We're talking tens of millions of weights and features, okay? So there's DrawCNN. This is a cool paper where they did visualizing of the different connections between the convolutional layers, and so I recommend going out and check that. That's not going to be on the exam, by the way. I'll talk about what might be on the exam at the end of the lecture. So the amount of computing required is gigantic for this stuff. So these techniques are only recently possible due to massive computing power. GPUs have become ubiquitous, very cheap to manufacture. Like a modern day GPU 20 years ago would have cost millions of dollars to produce. And so what we do with GPUs is your CPU might have, I don't know, what's a CPU like today? Like 8 cores or something like that? You can have more. Let's say you have an 8-core CPU, 16 threads. Each of those might be a few gigahertz, maybe up to like 3 or 4 gigahertz. But a GPU is going to have something like 1,200 to 3,000 processors in it. Now, they might only be operating at a couple of hundred megahertz, up to a gigahertz maybe, but you have so many more of them that you have so much more processing power overall. And neural networks are massively parallel. You can do like all the calculations for a single layer at the same time without needing to wait for any pipelining or anything like that. So you have a CPU which may have a few cores, but your GPU is going to have like hundreds, if not thousands of cores now. And what we can do is we could take, for example, the entire layer right here, because it only depends on inputs from its left. And so we could do all the outputs for this layer in parallel at once. And then once those are done, we do all the outputs for this layer at once. And then once those are done, we have all the outputs for this layer at once. So if you have a number of processors equal to the number of outputs at a given layer, then you can do the entire layer like that, right? It's really, really massively parallelizable. Autoencoding. So something that also happens is called autoencoding. So let's say we have some inputs to our neural net, x1 through xn. What we have over here, this is the general structure of an autoencoder. An autoencoder is going to take some input from the input layer, then it's going to have one, possibly more hidden layers, but let's just say it's going to have one hidden layer, and then an output layer, which is the same size as the input layer. Now, the key to an autoencoder is that the hidden layer is smaller than the input layer. So, the hidden layer is smaller than the input. The output layer is the size of the input. So our target values are so how do we train this, okay? What we're trying to do is the following. We're trying to pass in, let's say, for example, an input image, okay? We're trying to pass in an input image through a layer that's smaller than it, and then the output values that we want are the input values. And so the training is really easy because we're trying to get the output to match the input. So who can sort of tell me what's happening here? If I pass a certain amount of data through a smaller tube, and then I expand it back out to try and get the same data back out, what's that process called in computing? You've probably done it 100 times in your life with software on your computer. What's the process of making something smaller and then re-expanding it called? Someone said JPEG, but probably trolling. But yes, compression. But JPEG is not far off because JPEG does do compression. And this is a form of lossy compression, meaning we won't get the exact input back out, but we will get something. So this is going to find patterns somehow and generalize the input so that we can indeed pass data through this layer and get something back out. Now, typically the hidden layer will be much smaller than the input and the output layer. But what we're doing is compression. So for example, here's some examples of images that have been autoencoded. So we're going to have an original image here, which might be like 64 pixels by 64 pixels. Our output image might be like this, but I think in this case, if I remember correctly, the hidden layer was just eight values, okay? So this went through like 8 neurons and then came back out the other side, and we have this you might say this is horrible compression, but it was compressed so small that this is pretty remarkable. Here we have another example, and this kind of does look like really bad JPEG compression, right? So the autoencoding sort of generalizes the inputs, and you can see this as a form of compression. And deep neural networks, they use autoencoders very frequently. So unlike our demo example, due to these generalizations, it's often difficult to understand exactly what the DNN is doing and what features it's extracting. Because if it's passing it through CNNs and then pooling and then autoencoding, like it's so difficult to intuitively visualize what's happening that there's an entire field of research dedicated to just trying to understand what's happening inside the neural nets. Now, conceptually, we understand that it's just math, right? We know all the math, but like how and what types of features it's actually coming up with is a little bit hard to understand in some cases. I had something else to say about this, but I can't remember, so it's okay. Dropout is another thing that happens. So, the curse of the neural net is that it can get stuck in local maxima. So, what dropout does is a technique for trying to A, not get stuck in local maxima or minima, and B, try to be more generalizable to different types of inputs. So what dropout is let's say if on every iteration of the feed forward of the network, we're going to flip a coin for each neuron. And depending on the output, we're going to disable that neuron or keep it. Okay? On the next iteration, we do the same thing and possibly drop out a different set of neurons. And so it prevents getting stuck. It can help prevent getting stuck as local maxima by turning off or on these neurons to sort of try and put us down a different path in the gradient descent. It can also help us by not overfitting to the training data, okay? So if we turn off and on different neurons, then this can help us be more robust to changes in input data. So for example, if we did all of our training on one very specific image of a goose or whatever, and then we hand in another one that's sort of like it but not quite, if we use dropout, we can handle more noisy changes to the input a lot easier. So this is what dropout looks like. We take our fully connected network, and then on the next pass through, instead of being fully connected, for each of our hidden layer neurons, we're going to randomly turn some of them off and some of them on. And then we'll randomly turn another one on or off as well, okay? And then we're going to do the back prop with those neurons turned off, and ideally, this is going to help us be more robust in our calculations. There's a generalization of dropout called drop connect. So if we look at dropout, what dropout really does is it turns off all the connections from one neuron to its... It turns off the connection from its outputs to the inputs of the next layer. So we can generalize dropout with drop connect. And what drop connect does is instead of dropping entire neurons, we're randomly dropping individual connections. Okay, and this is used for the same purpose. Okay, so that's just some of the things that are used in deep reinforcement learning. However, one of the most important things, in deep neural networks, those are just some of the things. So let's tie neural networks into reinforcement learning. And I had this question before in class, and the question was, you remember when we did remember when we did Q learning? I'm getting ahead of myself. When we did Q learning, someone out there type in the chat what the main problem with Q learning was. Like, we have a table, right? We have a table of values. What's the problem with storing a table of values? What's the problem with storing a table of values? Someone said it before. If you don't get it, it's okay. So no one said anything, but the problem with storing a table of values is, what if our state space is too large? Right? What if we have more possible states than we have inputs? So let's look at that problem. So tabular reinforcement learning is like the Q learning we're doing on assignment 5. We have this Q table, right? It's an array that stores values for all of our states. But in our assignment, we just have 100 states or 200 states or something like that. So we can store an array that stores 200 values. But if we move on to like sort of real world problems or video games or chess or Go or something like that, tabular reinforcement learning can't possibly work for that, because there might be trillions or gazillions or universe-sized number of states. And there's a discrete state representation, and it can only work for low-dimensional data. So what we want, ideally, is instead of using a discrete table, we would want a function approximator, right? So we have this Q value, Q of SA. That is a lookup table in our assignment 5. But what if we had a function that could estimate Q of SA that didn't store all its values in a table? So what if that was the result of a function and not of a table lookup? Well, the function doesn't have to be that large, right? If it could compute the ideal value. It doesn't have to store all the values if it could compute it. But now we know that deep neural networks are really good at function approximation. So if we take a deep neural network and we use it as the function approximator for QSA, or Q of S, or whatever we're trying to learn about in our reinforcement learning, then what we're doing is, if we replace the table in tabular reinforcement learning with a deep neural network, then we're doing deep reinforcement learning. So let's take a quick look, a quick hand-wavy abstract look at deep Q networks. So deep Q networks, we're going to use deep convolutional neural networks for function approximation to approximate the optimal value of Q star of S of A. So remember, that's the true value. And we're going to use a modified version of Q-learning that changes when some updates are performed in order to encourage convergence. So there's a paper here that's really good. It's about Atari and deep Q networks for playing Atari. Here's a link to the paper. It's called Human Level Control Through Deep Reinforcement Learning. And literally what it does is it uses an algorithm very similar to the Q-learning algorithm that we know, except it uses a neural network to compute the values of QSA, and it used backpropagation as like the update function. Know how we have an update function to update our values? Well, where we use like alpha, etc., it's going to use a combination of that in conjunction with the backpropagation to make sure that it converges to the right values. So I'm not going to read all of this, but this is just a screenshot from the paper, and this is the update function for DQN, or deep Q networks. And if we look at it, look at this. Look at how similar this looks. We've got R, that's our reward, plus gamma times the max A, or max A prime of Q SA prime, right? Minus Q of SA. This is almost identical to our update function for Q learning. But what it's doing here is it's using this as the error function for its backpropagation. So it's learning to store the state action values in the neural network instead of in a table. And so that's how it's able to do that. Because you could just have a bunch of inputs to this neural net, and the neural net does not have to have one neuron for every possible value. We saw how neural networks work. And so you could have a neural network, and in just a few megabytes, it might be able to closely approximate the actual state values, state action pair values, for a much larger game. So what they did for the game of Atari is they had the following policy network. Okay, so this is a policy network now. They're not storing values, they're actually computing the actions. So let's say, for example, schematic illustration of the convolutional neural network. The details of the architecture explains in the methods of this paper. The input to the neural network consists of 84 by 4 image produced by the preprocessing map, followed by 3 convolutional layers. And so what that meant is that I think this was from the Atari paper, and the Atari paper had the pixels of the image, like the red, green, blue, 84 by 84. I think it was from Atari. And they passed that through 3 convolutional layers Okay? Those went into a fully connected network, and then the output that they were trying to do from the neural network was what combination of buttons should you press. So for example, you could do this in a supervised learning sort of way, where you say watched a human play and you had the human replays, and your input would be the state that the human was at, and the training data that you're trying to learn is what output or what controls did the human do at that state. Or if you're doing reinforcement learning, you could try a bunch of different actions, and then you could update the values of the value network in a similar way. And this is sort of what AlphaGo did. So now we're sort of at the point where we can understand, at least intuitively, what AlphaGo did. So AlphaGo, again, in case you didn't know, is Google DeepMind's Go program, its AI system, that beat the world champion, Lee Sedol, at the game of Go in 2016. It was huge AI news. So AlphaGo combined deep learning and heuristic search, a specific type of heuristic search, what you could understand it. So two networks were trained. You have a value network, and that's how good the state is, and a policy network, which is what move to do at a state. So it had tens of thousands of human professional games to learn from. And so in the policy network, which I just talked about, the input value to the neural net was the state. So it was like, essentially the neural net would look something like this. Let's say we have our neural net inputs over here. Okay. Then for every piece on the board, it would essentially record like a value, whether it was blank, it was white, or it was black. And those are the inputs to our neural net. And that's exactly what it did. And it turns out that convolutions are super good at this because Go looks like an image. It looks like a black and white image. So these edge detection things, it just worked out absolutely perfectly because Go, in its essence, is a two-dimensional image, and it turns out that convolutions are especially good at processing things that look like two-dimensional images. So they learned this policy network. The target was the move that the human performed, and they used the value network. The input was the state, and the target was who won the game from that state. And once it learned what it could from humans, it played against itself. And when it played against itself, it continued to learn and get stronger, and now it learns from a stronger opponent each time. And so it's crazy, you know, like this is something that computers can do really well, is sit down and play billions and billions of games against itself and get better and better and better way faster than humans can. And so also key was to throw in some random moves or random states in order to learn about things that you might not, some states that might not be visited if humans were to play against each other. AlphaGo 0 or Alpha 0 learned entirely from self-play. It used Monte Carlo tree search to play the games against itself, and then it learned which moves were good by using deep reinforcement learning. So it converged faster and also used less computation than the original AlphaGo, and it also worked for chess as well. So I'm not going to read out all of this. You can read this from the slide. But I just want to show you here that it did use some Monte Carlo tree search and combine that with reinforcement learning for its state evaluations or its heuristic functions. So Go has a very large branching factor. And so the reason why heuristic search doesn't beat professionals at Go is because you can't have, for example, a branch with like 300 moves like this and then 300 moves. Like, what's 300 to the power of 10, right? It's gigantic. And so the way humans play Go is they do some search, but they have really good abstractions for which moves are good and which moves are bad. And so what AlphaGo did was it learned a policy network. So it learned a network in which it said, okay, maybe these 4 moves are the only good moves for this particular board. And so now, instead of searching 300 moves, it just searches those 4 moves. And so it narrows the heuristic search to only consider the moves in the policy network, and so it can search much, much deeper in the network. And search also ideally needs some good evaluation function, right? Once you get to a terminal node in the search, you've got to be able to say this is a 7 or this is a 0.1 or this is a win. And so what it did is it learned the value network and used that for its heuristic function. Really, really intelligent, like really smart way of going about things. It combined the power of search and it combined the power of learning. And now at the end of the course, you're starting to see why that's so powerful. Excuse me. So not only did Google do this with AlphaGo, but the researchers at the University of Alberta did this with the DeepStack Poker AI. And so the DeepStack Poker AI, they took in different card ranges. They did bucketing on those cards. They used a feed-forward neural network for actually learning a value function for those hands. And then they did something which they did like this thing called counterfactual regret minimization, and then they put Monte Carlo tree search on top of this. I recommend going to read the paper for all the details, but the important part is that it used search and learning for this process. Now, one last thing I will say is that deep neural networks are not perfect, okay? What they are doing is mathematics, and what they get out are these discrete values. So for example, you may see the exact same image here, right? But when we talked about like how neural nets actually work, they take a bunch of values multiplied by a bunch of weights and then sum them, right? And then they pass that through an activation function, and then they get some value which might be high or it might be low. So if one of these input pixels is only slightly different, maybe it's like an off shade of red instead of a deep red or something like that. Maybe now we're here in the activation function instead of here, and we get a 1 instead of a 0, and our output gets completely thrown off. And this is something that can happen to deep neural nets. So here's just some examples. So this process, this paper, used, I think it was GANs, to do training, and what the network trained, it trained itself to find images that tricked deep neural networks. And so, for example, by taking this input image and fuzzing it with this amount of noise, you get this image out, and the same network that correctly predicted all of those images in the past, now it thinks this is an ostrich. It took this image of like a pheasant or something like that, or a grouse. It learned that we distort it with this, and now we think it's an ostrich. So these were all correctly identified beforehand. And in the middle here, a new network was trained to defeat this network and made it incorrectly classify all these things as ostriches. So not only did it tricked it into doing what it wanted. And so, oh my God, think of the possibilities here. What if Tesla has a neural net to identify a car from a truck, or a truck from a grandmother or a baby, right? And someone gets a hold of its training data, and now it's like training, you see what could happen here, right? It's defeatable. It's not perfect. And so what they try and do in order to protect against this is like apply like Gaussian blur to the whole image before they pass it through the neural net. And that way it's not so susceptible to this like tiny bit of noise. But over here, for example, we get new things over here where it just said, I'm going to make it incorrectly predict everything as an ostrich, right? So yeah, there's something to be said for analog cars and the hacking that's going to happen at an industrial scale once everyone's driving self-driving cars is going to be crazy. All right. So here's another example of some data. It thinks this is a robin, this is a cheetah, this is an armadillo, and this is a panda. Can you pick those out? I can't really pick those out. It also did some cool ones where it made it like it tricked it into thinking that these sort of abstract designs looked like a specific animal. So this, it thought it was a king penguin because it's got some gray, it's got some black, and it's got some, like, if you think about what it's doing under the hood in the identifying of these features, maybe it just says, well, if there's a transition from gray to black and there's like for example, over here, this kind of looks like a penguin, doesn't it? Where it's like, it's got a belly right here. Let me draw the penguin that I see. So this here is like the back, this is the belly, and that's the beak, right? So that kind of looks like a penguin, maybe. You can definitely see why it thinks this is a baseball, right? Because it's got the pattern of a baseball in it. That's like the texture map of a baseball. I can't see an electric guitar here, but that was the closest thing in its training set. Similar with this starfish. Maybe the starfish had some of these patterns of the colors. So neural nets are not human. Humans can be tricked. You've all seen an optical illusion, right? So you've all seen an optical illusion, so your eyes can be tricked just like a deep neural network can be tricked. So deep neural nets are an amazing feat of engineering and science that produce spectacular results, but they're not magic. They're mathematics. And because they're mathematics, they're function approximators that take some input and learn to produce some output. You could then learn what tricks them. Okay, so that's just my last message for the day, is that deep neural nets are incredible, but they're not perfect, and they can be fooled. Heuristic search cannot be fooled, right? You can't write alpha beta. You can't have alpha beta search magically not work because you tricked it somehow, right? But anyway, I'm not going to get into that whole debate. What I'm trying to tell you is that a lot of people would have you believe nowadays that deep neural networks are all of AI. And that's not true whatsoever. And now you can see some examples where they shouldn't probably be used. Okay, that is actually the lecture for today. Essentially, what is in these slides can be fodder for the exam, all right? So I may ask you something like, why are convolutions used? For a long answer question, right? So you could regurgitate what I said there, or other things. All right, so that's it for today. I really thank you. So some people are commenting in the chat that there are other AI techniques that I did not cover in this course. Someone mentioned hierarchical task networks. Someone mentioned fuzzy logic. Someone like expert systems. There are 30 different techniques that I could have covered in this course. I chose the ones that I felt I wanted this course to tell a story, okay? I wanted us to start with exhaustive brute force search, working into heuristic search, tying that in with some game theory to do multiplayer search. Then we got into genetic algorithms to see what they do well. And then in the end, we have reinforcement learning. We see what it's good at, and then we see at the end that you can tie all of these things together. You can have genetic algorithms which help shape your neural net, right? You can have search which is guided by neural nets. You can have neural nets whose training is sped up by different forms of, I don't know, whatever, maybe genetic algorithms. It's really fun to combine these systems. And if anyone tells you that this one system is the best, they just don't know what they're talking about. Because like someone in the chat just said, the best systems so far have been the one that use hybrid techniques. Okay, so that's where I'm going to end it right there. Next week, what we're going to do is we're actually going to watch the AlphaGo movie. I cannot do that on Twitch. So what I'm going to do is I'm going to allot you the time to watch the AlphaGo movie, and I have permission to distribute it to students only. So unfortunately, if you're watching this and you're hyped for the next episode, this is probably the last lecture that the public is going to want to watch, because the next two lectures are going to be the movie. And now that you know all of this stuff, you can actually appreciate that movie. And then the very last lecture is not going to be live streamed. I'm going to hold it on Discord, and I'm going to talk about the exam and give some sample questions and stuff like that. And I'll be around to answer questions about the exam or about the final assignment. So if you're watching this on YouTube, I think that might be where we end this. And I want to thank you for coming along on this intro to AI with us. I certainly had a lot of fun. And I really appreciate you showing up, especially for the people in the course, but also especially for the people not in the course who gave me lots of great feedback and said that they really enjoyed things. So thank you very much. And I will see you next term with Computer Science 4303, which is an introduction to artificial intelligence for video games. So we're going to take cool stuff from this course, cool stuff from the other course, and create like this really cool course where we talk about cool stuff like procedural content generation and more net pathfinding and navigation, and we have a cool final project with StarCraft or Minecraft or something like that. So thanks again for everyone for tuning in, and I'll see you next time.